Welcome to the latest episode of Star Cells and God. My name is Fuz Rana. I'm a biochemist and a Christian apologist, and I'm joined in studio today by Dr. Hugh Ross, who is an astronomer, a Christian apologist, and the founder of Reasons to Believe, which is the organization that sponsors this program, thanks to the generous gifts and donations of viewers and listeners like you. Today, Hugh and I are going to be talking about two discoveries that involve the origin of life question. Hugh's going to be talking about the discovery of nucleobases in an asteroid called Ryugu, and I'm going to continue in the origin of life theme by talking about the creation of a 45 nucleobase RNA self-replicator. Both discoveries are claimed by the researchers to provide evidence for chemical evolution, but Hugh and I are going to offer a critical perspective and show how these discoveries actually provide evidence that apart from the role of a creator, life cannot originate on Earth. So you don't want to miss this episode. Well, Hugh, it's always fun to be in the studio with you. I don't want to delay any further. Why don't you go ahead and take it away? Talk about the discovery of these nucleobases.
Well, a few days ago, Nature Astronomy published a 36-page paper by a team of Japanese astronomers based on their analysis of a sample that was returned from the Hayabusa 2 spacecraft. I mean, Ryugu is an asteroid that was named after a Japanese astronomer that discovered it.
Okay.
So the Japanese felt, hey, we got to go there. So they actually sent a spacecraft to go to the asteroid. It's about, 900 meters across.
Okay.
So about half a mile across. So it's a relatively small asteroid. But they sent a spacecraft there that landed on it, took a sample, and returned to Earth.
That in and of itself is remarkable technology.
It really is. And they wanted to come back with 3 samples. They could only come back with 2 because they were concerned if they went for the 3rd sample, it would do some damage to the craft. They wanted to, hey, we got 2. We know we're good. Yeah. Let's not take any risks and bring it back. And now, it's not quite like the Apollo program where they brought back, hundreds of kilograms of rocks.
Right.
This was 5.4 grams total. So kind of a tiny sample. I mean, you can hold it in the palm of your hand. But by bringing it back to Earth, they could use really sophisticated analytic equipment to basically look for abundances of levels that would otherwise be impossible.
Yeah.
So that was the whole point. I mean, if they tried to do it in situ,
right,
they just wouldn't get the precision. So bring it back to Earth. And this was a 7-year mission. So, because it took a while to get there, and it took a while to come back.
Yeah.
But they did successfully deliver 5.4 grams of material from the Ryugu asteroid. And it was a carbonaceous asteroid,
okay,
which means it's going to be filled with all kinds of carbonaceous molecules.
Yeah.
Molecules are going to be very interesting for the origin of life. And this got published online a few days ago, so it's not yet in an issue. But they said, hey, this is so important, we need to release it in advance.
Yeah.
They did that, and you should see the explosion it caused on the internet. I mean, there were scientists who were commenting on the discovery, but a lot of lay people weighed in too.
Right.
And kind of the news that's been thrown out there, reason why we're discussing it, they're saying this solves the RNA World Hypothesis, rescues the RNA World Hypothesis.
Sounds familiar because that's what I'm going to be talking about.
That's where you're going to be talking about.
Too, about a discovery that rescues the RNA World Hypothesis. But go ahead.
Well, didn't mean to steal your thunder.
No, you're not. But
this is a different proposed solution, and it's all based on the fact, hey, there are 5 nucleobase molecules that make up RNA and DNA, and they said, we found all 5 in this asteroid. And what really got them excited is they found all 5 in very roughly equal amounts. I'll give you the amounts in a minute. But when they've looked at the Bennu asteroid, also returned a sample, and what they discovered is, let me give my notes here. With Bennu, because the nucleobases fall into two categories, the purines and the pyrimidines. I mean, you're a biochemist, you know all about this. But what was disturbing to the origin of life community, the sample that came back from Bennu, they had the pyrimidines, but not the purines. Well, that's a bit of an exaggeration. They had purines that were less than 1/10,000th the abundance of the pyrimidines, which is going to be a problem for the origin of life if you got them that different. And then there's two meteorites that they recovered here on Earth, the big ones. Murchison is the biggest carbonaceous molecule. And when they looked at Murchison, they found the opposite. It had the purines, but not the pyrimidines. And Bennu and Orgiel, which is another meteorite, the purines were missing.
Okay.
So what was exciting about this discovery is, hey, we got both.
Yes.
And not in equal amounts, but in amounts where you can't say there's a problem where one set is missing. So that's what got all the excitement. And they said, hey, given that we got all five and one asteroid, this solves the RNA World Hypothesis. And, you know, we've been talking about this for literally decades. It's the hypothesis that naturalistically you get RNA molecules first, and then sometime later the RNA molecules will evolve into DNA, proteins, membranes, and RNA. So RNA comes first and basically evolves and differentiates into all these molecules. And we've been attending origin of life research conferences. A lot of attention was on the RNA World Hypothesis.
Yeah, well, you know, it's interesting is we're going to probably discuss there is a lot of genuine scientific problems with the RNA World Hypothesis, but origin of life researchers simply can't abandon it even in spite of all these problems, and it's because it solves what's called the chicken and egg paradox.
Yes.
Is that we live in a, you know, the biochemistry today is based on DNA and proteins. And so DNA, even though people say it's a self-replicating molecule, it really isn't. It can be replicated, but it requires the cell's machinery to do it, which is made up of proteins, right? And those proteins to replicate the DNA are encoded in the DNA, and it takes proteins to make the proteins. And so you have this interdependency that is impossible to solve from an origin of life standpoint.
And it takes the RNA to transfer the information back and forth.
Yeah, right. Yeah, it's playing an intermediary role. And so the way around it is to say, well, RNA can do both. It can store information, and it can also function like proteins. And this is based on the discovery of what are called RNA enzymes or ribozymes. And so, you know, that's why people can't abandon it, is because there's no other way to...
It's really the only game in town, so from a naturalistic perspective.
Right. So a discovery like this is very exciting to origin of life researchers.
Well, I read through the paper, and what's interesting is that the researchers are astronomers trying to do biochemistry. So it kind of indicates the relationship that we have here. So our disciplines can't help but overlap. And that's what they discovered here. So, but I read through the paper and said, where's all the data? Well, the data was online. You had to kind of go off and get the supplemental data. So this is the table of all the data they got there.
Okay.
And I said, you know, they put all the data in picomoles per gram. And it's like, I don't think lay people are going to be able to work with that. So I wound up converting all the picomoles per gram into parts per million, and actually discovered, hey, it's got to be parts per billion, because it's not like what we see in Murchison, where we're getting a few of the bioactive amino acids at parts per million. These are parts per billion, and I'll give you the numbers. The cytosine, 0.7 parts per billion. Uracil, 2.9 parts per billion. Thymine, 3.0. Adenine, 6.2, guanine, 7.9, which I thought was interesting. The ones that got more atoms actually have a higher abundance level than those that don't.
Well, one problem is cytosine is actually not a very stable nucleobase, so that's probably why it's
so low. Right. So, but yeah, we're looking at parts per billion, not parts per million. So, but what's interesting is that you're getting all five at roughly a part per billion. So, I mean, it is different than what you're getting in Bennu and Horgiel and Murchison, where you're seeing you only get a few of them, and the others are virtually missing. But if you dig down into the table, they say, well, these are the 5 bioactive nucleobases, but there's a whole bunch of other nucleobases that are not bioactive. And then you've got things that look very similar to the nucleobases. And so I looked at the ratio of the bioactive nucleobase abundances that they found. They were compared to the total of the nitrogen heterocycle molecules. And the ratio is 9 to 1. So there's 9 times as many non-bioactive nucleobase and nitrogen heterocycles as there are bioactive nucleobases. And this was never discussed in the paper. 36 pages, like there's a dilution problem here.
Yeah.
If you're going to claim that this is going to solve the origin of life problem, which is a claim that was made in the paper, it's a claim in every web article I've seen commenting on it, is that if you're going to claim this is going to solve the problem, how do you explain the fact, you got these bioactive nucleobases. Number one, there are really low abundance levels.
Yeah.
How is that going to help an origin of life scenario when the abundance levels are so extremely low? And number two, if you're going to have any kind of naturalistic chemistry going on, all these other, nitrogen nucleo heterocycles, they're going to get in the way.
Yeah.
They're going to interfere. So it's not like what you're doing in an origin of life simulation lab where you get rid of all the stuff you don't want messing up the experiment.
Right.
And basically just go with the stuff that you want. That's not the way nature works.
Yeah.
So I kind of bottom line is I don't think this really solves the, it doesn't solve the origin of life problem, and it doesn't rescue the, what is it called? The RNA World Hypothesis. And Fuz, you and I were in the second row when we heard Leslie Orgel, who was the father of the RNA World Hypothesis, give a lecture at one of the ISIL Origin of Life research conferences. Yeah. And it was the opening lecture. And I remember him pacing back and forth in front of us saying, I sure hope there are no creationists in the audience for what I'm going to say next. It would take a miracle for an RNA molecule to appear on the Earth. Just one molecule to appear on the early Earth. And basically spent his hour-long lecture pointing out all the problems in the RNA World Hypothesis. But he ended his talk by saying, we got nowhere else to go. We got to figure some way to deal with these intractable issues. That was 1999. The number of intractable issues has gone up, not down. And moreover, we're dealing with nucleobases that are quite simple compared to some of the more complex amino acids. I mean, I looked at the number of atoms. They run from 12 to 16. Guanine, the simplest of the amino acids, is 10. All the others have more. And, back in 2011, I wrote an article, it's up on our website, about the problem of missing basic amino acids. And lysine and arginine are 2 amino acids, crucial bioactive amino acids that are basic, which means they have a high pH. And they said all of our simulation experiments, if we do them at temperatures 0 to 200 degrees centigrade, we get nothing. If we do them at 200 to 800 degrees centigrade, we get nothing. So they're basically saying, we can't even make this in the lab. So it's like, how is nature going to make these? And the paper ended by saying, okay, is it possible to conceive of life that has only 18 amino acids instead of 20? Can we conceive of life where we don't have these basic amino acids? And what they pointed out, you can't get the DNA to be assembled if those basic amino acids are missing. You can get proteins, and they showed you can get 61 functional proteins without lysine and arginine, but you got to have the DNA, and you can't manufacture the DNA without the arginine and the lysine. Now, that was published, the paper was published in late 2010. What I did yesterday, I went through the whole scientific literature and saying, is there any update? where people have kind of looked at this.
Yeah.
Is there an experiment where they say, hey, we found a pathway? And I discovered, no.
Yeah.
This is the only paper in the published scientific literature that deals with the problem of lysine and arginine. Yeah. So I thought, hey, maybe in 15 years the problem's been solved, but and there's been literally thousands of papers published on these basic amino acids, and not a single one. Yeah. So the problem still stands.
Yeah.
So.
Yeah. I think your points are very, 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 very cogent. Because when people discover, compounds that are relevant to the origin of life in asteroids, they oftentimes will argue, well, maybe there was extraterrestrial delivery to the Earth. But as you're pointing out, the levels are so incredibly low in the asteroid that if it did deliver these materials to the Earth, assuming those materials survive the impact, the dilution now that happens with regard to the Earth's oceans or just the Earth's surface is going to be so extensive that the problem is even compounded.
Yeah, we're not looking at parts per billion. We're looking at parts per quadrillion.
Yeah.
And now you got a real problem.
Yeah.
Another problem that did get pointed out in the paper, what if only a small fraction of asteroids have all 5 nucleobases in them?
Yeah.
I mean, when we looked at Bennu, it was missing the purines. And so if you don't get all 5, you're in trouble. But as you point out, there's a second dilution factor. Yeah, the asteroid has them at parts per billion, but once they get to the Earth, it's going to be diluted by everything on the Earth. We're looking at parts per quadrillion, which means it's hopeless for any kind of naturalistic origin of life scenario.
Sometimes, too, you'll hear people say, well, this asteroid might be a proxy for what could potentially happen on the early Earth. But again, the fact that this seems to be anomalous with regard to the fact that it shows the 4 nucleobases suggests that, well, there's other scenarios where you're not getting the nucleobases. And even then, you're still looking at such extremely low levels that and they're diluted out by other, interfering components that this is really irrelevant to the origin of life.
Yeah, and that might be nailed down because the paper ended by saying, look, we've gotten samples back from just 2 asteroids. We know the technology works. And, a database of 2, it's really hard to make any kind of statistical argument. Fair. So what if we get, say, 10 or 15 samples from asteroids, from different asteroids? Now we'll know, for example, is Bennu exceptional, or is Ryugu exceptional?
Right.
We don't know that. And also, what are the sizes of the asteroids? And what they do address in the paper, we still have to solve the chemistry problem.
Yep.
Because they're making the point that ammonia participates in a different way to make the purines than the pyrimidines. So they said an unanswered question: how do we explain the fact that all 5 show up in this asteroid, given that you need 2 distinct chemical pathways to make them? That, to me, suggests that Ryugu is exceptional, not Bennu.
Yeah.
Bennu is kind of more in line because you only need the one chemical pathway there. So if I were to make a prediction, my prediction would be that if we do get samples from, say, a dozen different asteroids, Ryugu will probably show up as being the exception.
Yeah. Yeah. And I think it's important to point out here that, chemistry happens, right?
Yes.
If there are potential chemical pathways that can reasonably take place on the early Earth, there's going to be some level of those materials that will form. That's just the way chemistry works. But I think what this study is really showing is even if there is very low levels of these nucleobases on Earth, it's not leading you to some confidence in chemical evolution by any means.
Well, I'm on record as saying we look at interstellar molecular clouds, which is where all these things ultimately come from, whether it's the Earth or meteorites or whatever. The ultimate source is these interstellar molecular clouds. And we've yet to find any nucleobases there.
Yeah.
We've yet to find any amino acids. We've yet to find any of the 5 carbon sugars. But I think you make a good point. We will find them.
Yeah.
We just don't have the technology to discover these molecules at the very low abundance levels that they probably exist. Yeah. So I think we need to be honest with people. Don't be surprised if there's a paper being published 5 or 10 years from now saying we found ribose in an interstellar molecular cloud, or we found glycine in interstellar molecular cloud, or we found one of these nucleobases. Yeah. I think they will. It's just that right now we lack that kind of spectral precision to detect these things at parts per billion. Yeah. But that's coming. That technology will come, and I think we should be able to find them at about a part per billion, certainly at, say, hundreds of parts per trillion. Yeah. That seems to be a reasonable expectation based on what we understand about the chemistry of these molecular clouds.
Right. You know, and of course, just because you have the nucleobases doesn't mean you're going to have pathways then to generate the ribonucleotides.
You got to put them together.
Yeah.
You know, it's like a jigsaw puzzle. Having a bunch of pieces doesn't help.
And then you still have to solve the whole problem, you know, getting the right chiral enrichment, right? The homochirality problem. So the problems are legion with the RNA world. So I guess this discovery is better than having no evidence for nucleobases, but it's not a far cry from really being compelling.
Well, it'd be a shock if they found no nucleobases at all, given the abundance levels they're able to do their measurements at, because we would expect that chemistry to be active. Yeah. The problem is you've got chemistry that produces these molecules. You also get chemistry that destroys them, which I think explains why the abundance levels are so low. Yeah. So you got a better shot with some of the amino acids, but I find it interesting that 10 of the 20 amino acids are still missing. Yeah. And again, I think we'll find them, but now we're looking at amino acids that have more than 24 atoms in them. Yeah. So yeah, they're going to be harder to find.
Yeah. Yeah. Oh, that was a great discussion, Hugh. Are you finished?
I'm all done. Yeah, okay. I'm basically saying, hey, we need God to explain the origin of life. Yes. Because it's not going to happen on an asteroid. It's not going to happen on the early Earth without God's intervention. Exactly. That's kind of my bottom line. Yeah. But it sounds like you got another nail to put in the coffin.
Yeah. Well, you know, I'm going to also talk about the RNA world, and this is now at the other end of the RNA world scenario, which is the idea that if you're going to have a viable RNA world, you have to have RNA molecules that can replicate themselves. And a few weeks ago, your wife, Kathy, addressed our staff, and she talked about the parable of Jesus of the pearl of great price, right? And if there is a pearl of great price, which is, of course, that pearl that's so perfect that the merchant sells everything he has to be able to possess the pearl. Well, if there's a pearl of great price when it comes to original life research, it would be discovering an RNA replicator, a molecule that can replicate itself. And, you know, this, of course, again, is necessary if you're going to have an RNA world. And there's a lot of work that's been done by original life researchers that I think is really fine biochemistry, by the way, where they use a technique known as in vitro evolution, and I'll explain how the technique works in a minute, to create a whole bunch of different ribozymes that have a wide range of metabolic activities that would be necessary to support an RNA world hypothesis, where again, you have to have RNA that's not only storing information, but is functioning in a catalytic way like proteins
Well, for the lay people listening to this, how complex are these ribosomes?
Well, the ribozymes are, the shorter they are, the better it is for an original life research program. So some of them are in the neighborhood of about 50 to 100 nucleobases in size. Now, they have made some RNA enzymes or ribozymes that can actually do some interesting things that move you towards discovering a self-replicator. One is that they have polymerase activity, which means you can add nucleotides to a growing RNA chain. They have discovered ribozymes that have templating activity where they can bind short strands of RNA to themselves. And then there's other ribozymes that can ligate, which means they can join two RNA chains together, right? And so these are very interesting properties, but there's not really been an RNA self-replicator that has all of those qualities. And
so you need the whole set, not just one.
And so the concern, too, is that these types of ribozymes typically are more complex. So it's not only a chain of RNA, but it has to fold into a three-dimensional structure. And that has to be a very precise, complex structure in order to carry out polymerase and ligation, or polymerase activity, ligation, and templating types behaviors. And they also tend to be well over 150 nucleotides in size. And so the original life research community is like, look, these two objectives are, really invalidate the quest for the RNA self-replicator because they're just too large. So this is where this paper comes in, published by a team from Cambridge University in the UK, where they actually created an RNA self-replicator that can genuinely replicate itself with a footnote or two, but also it's only 45 nucleotides in size. And so that's what makes everybody excited. And just like the discovery of the nucleobases in the asteroid you're discussing, this was an internet sensation too, where again, the claim was we've solved the RNA World Hypothesis. We've got greater reason to think that this is a credible idea. But the bottom line is that when you really look at what they've done, it raises serious questions about, is the work even relevant to an early Earth? It lacks geochemical relevance. It's not prebiotically relevant. And in fact, when you examine the work in detail, it really provides, I would argue, empirical evidence that you need a creator if you're going to have an origin of life.
Well, you just said they need a whole bunch of nucleotides, and that means you need the nucleobases.
Right.
And if you don't have the nucleobases, you're out of luck.
Yeah, but let me go ahead and show the first slide. This is a little bit technical, and I apologize for it, but it really is central to the point that I want to make. And this is a technique known as in vitro evolution, in vitro in the glass. It's evolution happening in the test tube. And there's a name for it, SALEX, which means systematic evolution of ligands by exponential enrichment. And so what this essentially involves is you're looking for an RNA molecule that has certain biochemical properties. Let's say it binds a protein or a small molecule. So what they do is they create a DNA library that has random DNA sequences, random nucleotide sequences. And typically they're creating something on the order of about 10 to the 16 different sequence combinations. And so then you take this DNA and you have to have what's called a primer and RNA polymerase, and you transcribe them into RNA molecules. Then there's some kind of selection that takes place done in the laboratory where you're looking for all those RNA molecules that will bind the molecule of interest. You come with some method to separate them out of the mixture. They then are reverse transcribed into DNA. That DNA is amplified by the polymerase chain reaction, and then you start it all over again. And you typically go about 15 cycles, and usually you can find an RNA molecule in that mix. So this is the general technique that these researchers used.
I understand, but what if you don't have a DNA RNA library to start with?
Yeah, well, I mean, their argument would be, well, you would have a library of random RNA sequences on the early Earth. But kind of to cut to the chase here, this is a very elegant laboratory technique, but it's irrelevant to the early Earth for a number of reasons. One is you've got to have enzymes. RNA polymerase is an enzyme. Reverse transcriptase is an enzyme. You have to have DNA polymerase, which is part of the polymerase chain reaction. So you're presupposing the existence of enzymes in order for this in vitro evolution.
And enzymes are complex proteins.
Right, and you're not going to have that available on the early Earth. What you're going to have are potentially random sequences of RNA, just granting that all the other problems we've talked about are non-issues. You have to have a library of RNAs, and you've got to have some means to select that. And the selection itself can be rather ingenious in terms of how they select RNA with particular biochemical properties. So this is a highly elegant laboratory technique that's very useful, but it is totally irrelevant to the origin of life. And so in this particular study, this is what they did in terms of how they did the selection. If I could have the next slide, please. So what they ended up doing was, again, this is incredibly complex. It took me the better part of a day to figure out what they were doing. It's pretty straightforward once you figure out what they're doing, but from the paper and the supplemental content, it took me a better part of a day. But what they were doing is they were creating essentially through DNA and then transcribing it into RNA, basically a DNA molecule that had either 1, 2, or 3 copies of about a 30 or anywhere from a 20 to 50 sequence of RNA. So they had duplicates of that. And then they had a random sequence as well. And that random sequence had a region at the very end that was going to function like the template. And then they took basically an RNA molecule that they created that was a partial double strand. So a longer sequence and a shorter sequence that paired together, where that empty place was where the RNA was going to bind from the ribozyme that they were looking for. And then they wanted to make sure that it could ligate the 2 strands together. So that's what they were looking for, was that ligation reaction. And if it ligated together, the RNA that they were using to select had a molecule called biotin, which is a vitamin B7, that binds to a protein called streptavidin. And they then took magnetic beads, coated it with this protein, so that they could then select out the RNA that would not only template, but have that ligation activity. And then because it was a magnetic bead, they could pull it out of solution. Now you've got the RNA molecules you want. And then you can then use reverse transcriptase in the polymerase chain reaction. And they added another step where they introduced other mutations into the DNA, and then they repeated that selection process. If I could get the next slide, towards the end of these, I think they did 11 cycles, they then did a twist to the experiment where they wanted to see if it had polymerase activity. So now, instead of just ligating, if you look at the figure below, they ended up having a bigger gap that would have to be filled in by polymerase activity in order to, and then ligation at the very end. So after 11 rounds of this evolution, they ended up discovering 3 ribozymes. The shortest one was 51 nucleotides in length. So they called it QT51, which stands for quite tiny. Biochemists are no more creative in their naming than astronomers are.
51 is quite an achievement.
Yes.
So
then what they did is they took this ribozyme and they started deleting nucleotides to see if they could make it shorter. And they were able to get something that was about 45 nucleotides in length. So then they took the ribozyme and they were able to show that it could actually replicate things like the hammerhead ribozyme, which is actually a ribozyme that occurs naturally in biochemical systems. And what's nice about it is you can measure the enzymatic activity of the hammerhead ribozyme, so you know that you've made it. So they were able to show that, we could actually take a complex 3-dimensional structure for an RNA molecule and replicate it, unwind it and replicate it and produce a functional ribozyme. They then did another set of experiments where they showed that this could actually make a complementary copy of itself. And then they showed that if they started with the complementary copy and the ribozyme, the QT45, it could actually make a copy of itself. But they couldn't get it to all work in one pot. You had to do it in two sequential pots. And so voila, they've got a self-replicator. Now, this isn't as impressive as it seems, even though this is remarkable biochemistry, because it took this ribozyme 72 days to produce a copy of itself, starting with the complementary sequence. And the rate of production was 0.17%. That was the yield. So it's extremely inefficient, and it took 72 days. Moreover, what they had to do is do the reaction in what's called eutectic ice, which is ice where you load it up with salt, which depresses the freezing point well below zero. This is necessary for two reasons. One is it creates what are called these interstitial phases where you've got liquid water dispersed within the solid water of the ice. And that creates high concentrations, which allows for the reactions to take place. And the cold temperature stabilizes RNA, which is not a very stable molecule. Right. Now, but to get the molecule to unfold, they had to heat it up. That allowed it to unfold, let the reaction take place, and they cooled it down. So they had to do this thaw-freeze set of cycles over 72 days to get this incredibly low yield. And then they actually had to use trinucleotides. They couldn't use individual nucleotides. They had to use trinucleotides, which stacked everything in their favor.
Okay, now I understand what the N20, N30, N40 says. I was going to ask you that question, but thank you.
Yeah. Well, and so they had to, again, use these trinucleotides that were chemically activated at the end. So this is, from a biochemical standpoint, an incredible achievement, right? But on the other hand, it's completely irrelevant to the origin of life. Where are you going to have eutectic ice where you're going to get this freeze-thaw cycle, where you're going to get activated?
It's going to run for 72 hours.
Yeah. And where are you going to get these activated trinucleotides from? It's just completely, unrealistic, let alone there's no way to imagine how something like this could evolve. What would be the selection pressure? You can create that selection pressure in the lab with this highly contrived experimental system, but you're not going to be able to do that on the early Earth. So this is interesting work, but it's irrelevant because there's no way to envision how this would...
Let me suggest, Fuz, where it is relevant. Number one, it took really intelligent, highly knowledgeable, very well-funded, technologically equipped biochemists to pull this off.
Yes.
And if they weren't controlling it every step, they wouldn't have gotten this self-replicating
that's exactly
molecule.
Right.
Which means someone as smart as them and as intelligent as them and as powerfully equipped as they are must have done it in the first place.
Yep.
So in one sense, I think this is highly relevant. They're basically showing that the God of the Bible must have been the one that pulled it together.
Yes.
Because look at all the resources that they had to bring to bear just to get the limited results they got.
Yep.
So it's irrelevant naturalistically, but it's very relevant in terms of demonstrating there has to be a theistic answer to the origin of life.
Yeah, that's exactly right. And that would be exactly my point, is that ironically this work that is designed to try to bolster chemical evolution, in fact, if you're looking at it objectively, really provides empirical evidence that intelligent agency needs to play a role in the origin of life.
Well, let me take you back to 2002. A gentleman sitting right in front of us at the Origin of Life Research Conference was Robert Shapiro.
Yes.
And there was an experiment nowhere near as elegant as this. It was being discussed by someone delivering a paper.
Jim Ferris, I remember.
Yes, right. and what did Robert say? He said, this is incredible chemistry. You guys have made an amazing achievement, but this is just intelligent design. He wasn't trying to promote the intelligent design movement, but he was saying, without intelligent design in controlling the experiment, you wouldn't have gotten what you've gotten.
Yeah.
So he again was making the point, this is not relevant to a naturalistic origin of life.
Yeah, well, that statement at an Origin of Life conference where you have a room full of atheists,
right,
went over like a fart at church, so to speak.
Right.
I mean, it was like the absolute wrong thing to say. And I can remember Jim Ferris's face turning different shades of red, progressively deeper and deeper red, as he was processing what Shapiro was saying. The fact that Ferris maintained composure was impressive to me.
Well, I thought he did, because you really can't deny what Robert was saying. I mean, he was making it very clear, hey, I commend you for what you've done in the lab, but what have you proven?
Yeah. So, I think the bottom line here is this, is that, the RNA world isn't really any more valid today than it was, a month ago before these papers were published. And
well, I would argue more definitively, I think because of these two papers, the RNA world is in way more trouble than it was 3 weeks ago. So.
And, again, if you are really open-minded, I think the evidence, consistently points to the necessary role of an intelligent agent.
Yeah. I was also impressed, though, that I imagine this is in your paper as well. The researchers are basically saying, here's where we can go with future experiments, future space endeavors to really nail this down. But I think what they're suggesting is basically making our point. The more we learn about this, the stronger case we're going to get. There's a supernatural explanation, not a natural explanation. And we've been demonstrating that for the past 30 years. So.
Couldn't say it better, Hugh.
Okay.
All right. Well, thank you so much for watching this episode of Star Cells and God. We would really love for you to weigh in the comments section. Let us know what you think. Let us know your perspective. We read those comments, though we don't necessarily reply to them. We read every one of them. And then also make sure that you go to our YouTube channel, Reasons to Believe, and subscribe so that you can be alerted the next time a new episode of Star Cells and God drops, which is every Wednesday. Also, you can listen to Star Cells and God using your favorite podcast app. And make sure that you share this video with a friend. And last but not least, the more that we know about science, the more we have reasons to believe in the triune God of the Bible.